To see how to assign nodes to pages more efficiently, let's step back and just look at the general problem. Let's say I'm going to add items A through Z to a tree. There's no reason to assume that they'll be added in order. So we have to assume they'll be added in random order. And the order that an item is added into a VST determines where it's going to be in that tree. So there's no reason to assume that A would be anywhere near B or C. And furthermore, if all we're doing for page assignment is putting the nodes into pages as they fill up in the order that the nodes are inserted, then we have to assume that the nodes are essentially in a random page as well. So one page might contain maybe this node and that node and that node. It's totally just determined by the order that the nodes were inserted. So you have to remember also that this tree is very, very large, and due to the random order of insertions, the disk pages are more likely to be shaped horizontally than they are to be shaped vertically. You might get lucky occasionally and get a little bit of reuse out of a page as you're traversing down the tree, down a path in the tree. But more likely, you have to assume that you're going to jump into a page, load something, and then jump out of it. So as the tree gets large, the number of pages accessed to traverse the tree is proportional to the height of the tree. In other words, if we have to go all the way down to a leaf node 1, 2, 3, 4 steps, it's likely that we're going to have to access about 4 pages. And you are likely to have to go all the way down to a leaf node in the average case, since the leaf nodes contain more than half of the total nodes. So on average, you're going all the way to the bottom or very close to the bottom of the tree to look up any node. So if the number of pages accessed is proportional to the height of the tree, then we need to reduce the height. And one way to do that is to balance the tree, but this one I'm showing here is already perfectly balanced, so there is no way to reduce the height of this tree any further, at least not for a binary tree. So the only other way to reduce the height here is to increase the branching factor, or make each node have more than 2 branches. So we would make the tree wider, but shorter. And here is a quad search tree that does just that. So instead of 2 branches at each node, we have 4 of them, which means when we're traversing this tree, instead of making a left or right decision, we need to make a decision whether to take branch 0, 1, 2, or 3. So with a binary search tree, you have a key and then you have a branch on either side. With a quad search tree, we still have branches on either side of keys, but if we want 4 branches, then we will need 3 keys. So a branch there, 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 and there. And the way this works is these keys have to be ordered in order to determine which branch to take. With a binary search tree, it's easy. You look at one object and then go left or right. With a quad search tree, let's say we're looking for E. Well, E is between the D and G keys, so we would take this branch and then look for E in that node. So it works, kind of the same way. It's just there are more keys per node instead of just one. So what does this do for us? Let's look at the previous example where we can fit 3 keys per page, just like the binary search tree example. But now, instead of a page containing multiple nodes, if it can hold 3 keys, then one node fills up an entire page. So every node here is exactly 1 page. And look at the height of this tree. It's only 2 levels, or a height of 1. So if we go back to the binary search tree version, it had 4 levels, or a height of 3. In other words, we have half as many levels in this tree as the binary search tree version, and we can now find any node in at most 2 page lookups. So let's say we're looking for H. We would load this page, decide to take this branch, and load this page, and now we've found H. And that's true for anything we're looking for. No matter what, it'll be 2 pages loaded or less. So what is the trade-off here? Well, in order to decide which branch to take, we have more computation per node. Whereas with a binary search tree, we only need to compare to one item to decide whether to go left or right. In a quad search tree, we need up to 3 comparisons to decide whether to take branch 0, 1, 2, or 3. But all of that computation is on data that is within one page. So the higher cost of loading that page from disk has already been paid, and then we're just going to do comparisons on all of that data in memory. And it's not like we are increasing the total number of computations we have to do. We're just doing more computations per node, but there are fewer nodes and fewer decisions that we'll have to make as we traverse down the levels of the tree, because there are fewer levels. So this is actually exactly the point, and this is how we're getting more reuse out of each page. We load a bunch of items and do a bunch of comparisons all at once within the one page, rather than doing them one comparison per node or one comparison per step, which may all be in different pages.